So we said at the beginning of the class that there are 5 mathematical processes that we're going to need to get very comfortable with vectors. The first 3 we've already used a lot at this point. So we know how to add vectors, we know how to subtract vectors, we know how to multiply a vector by a scalar. The 2 other processes we have are basically different ways that you can effectively multiply 2 vectors together. The first one is you multiply 2 vectors together that gives us back a scalar, so this gives us just a number. And then we'll also learn how to multiply 2 vectors together that gives us back a vector. But the one we're going to deal with first is the dot product, or the scalar product, again, just to emphasize what you get back as the output. And that's a way of multiplying 2 vectors together that gives you back a scalar. So that's the next mathematical process that we're adding. So there are a couple different ways that we can talk about dot products. The first first way is we'll talk about the algebraic rule. So basically, if I've got 2 vectors, so here's vector A, axi hat plus ayj hat plus azk hat. Here's vector B, bxi hat plus byj hat plus bzk hat. Their dot product is just axbx plus ayby plus azbz. So notice a couple of things to emphasize here. One is there aren't any unit vectors anymore. This isn't a vector at all. It's a scalar. So these are just taking the components. So here's the x component of A times the x component of B, plus the y component of A times the y component of B, plus the z component of A times the z component of B. So components are just scalars. And so all we're doing is basically multiplying scalars together and then adding those products. That's what the dot product is. So fundamentally, the dot product of 2 vectors is the sum of the products of the corresponding components of each vector. So if you've got 2-dimensional vectors, then you're going to have 2 indices, say x and y, that you would sum together. If you've got 3, you're going to have x, y, and z. So all you're doing is just multiplying together the component products and then adding those together. That's the algebraic rule for dot products. One of the nice things about the algebraic rule is we're pretty good at this point at breaking vectors up into components. So it's fairly easy to break a vector up into its x, y, and z components and then go ahead and just use this rule to multiply it out and get the dot product. There's also a geometric rule for dot products. And so if I think of 2 vectors, here's vector A, the red one, vector B, the blue one. And notice I've got this angle here that's called phi, and phi is very clearly marked as the angle between vectors A and B, right? So I've just drawn in the angle between them. I can also calculate the dot product by taking the magnitude of vector A times the magnitude of vector B times the cosine of the angle between them. So AB cosine phi will also give me the same value as axbx plus ayby plus azbz. So part of what this geometric rule is hinting at is, well, so I can sort of group these terms up, right? So I can sort of combine the b and the cosine phi. And again, if you think about what b cosine phi is, well, that's just this parallel component of vector A. And then there's a perpendicular component that would be b sine phi, but this component doesn't end up in the dot product. So one way to think about the dot product is it's the magnitude of vector A times the component of vector B that lies along the same line as vector A. Or I can switch this around, right? I could put the cosine phi with the A, and then again, notice what I've got then is I've got a cosine phi would be this parallel component to vector B. There's also a perpendicular component that would be the a sine phi, and that doesn't show up in the dot product. So what I get either way, right, there's nothing sacred about which vector I choose to sort of leave alone and which one I choose to turn into components. But either way, what the dot product is telling me is how much 2 vectors lie along the same line. So the dot product is giving us information about how much 2 vectors overlap. So do they lie along this? How much do they lie along the same line? And what's the relative direction of that? So here for A and B, they both pointed in the same direction along a single line. So what does that mean in terms of the dot product telling us about the relative orientation of two vectors? Well, if we think about our geometric interpretation of the dot product, right, the magnitude of A, that's always positive. The magnitude of B, that's always positive. So the sign of the dot product, and again, as a scalar, this can be positive, it can be negative, it can be zero. But whether it's positive, negative, or zero is really all about what's going on with this cosine term. And that means that it very much depends on what the angle phi is. So the option we were just looking at was a situation where the angle phi was less than 90 degrees. And in that case, our dot product was positive. So if the relative orientation between these two vectors is that they have components that point in the same direction, the dot product between them will be positive. Cosine phi is 0 when phi is 90 degrees, right? Cosine of 90 degrees is just a fancy way of saying 0. So if my two vectors are perpendicular to each other, then their dot product is 0. So one of the things the dot product lets me do is it lets me figure out whether or not two vectors are perpendicular to each other. I simply calculate the dot product, and if it's 0, then they are. My third option is, again, I can have an angle phi that's larger than 90 degrees. So here's an angle phi that lies between 180 and 90. And again, this now gives me a dot product that's negative. So it says that the component of B points in the opposite direction as the vector A. So when I think about the component of B that's parallel to A, it points to the left, A points to the right. So again, it's telling me about the relative orientation of those two vectors in terms of thinking about, do they point in the same direction, perpendicular to each other, or in opposite directions. And that is simply denoted by this sign. If it's positive, they point in the same direction, or at least have components pointing in the same direction. If the dot product is 0, those two vectors are perpendicular. If the dot product is negative, then their components point in opposite directions. So there are sort of, three special cases that we can think of then. The first is when the angle between those two vectors is 0, which means A and B point in the same direction, and that's when I get the largest dot product and it's positive. So the largest possible dot product I can get back is just going to be positive magnitude of A times magnitude of B. Again, when those two vectors are perpendicular to each other, like we've already seen, that means my dot product will be 0. And when they point in opposite directions, now the angle between them, phi, is 180 degrees. Cosine of 180 degrees is just another way of saying negative 1. So I end up with negative magnitude of A times magnitude of B. So I can get, my dot product can give me back any value between plus AB and minus AB simply by changing the orientation of those two vectors. So basically changing the angle phi will change what the value is of the dot product. And so it can be as large as positive AB, it can be as small as negative AB, it can be 0 in between. All those are options.